Good evening, everyone. So today in this session, we'll be starting with the chapter circular motion, right? We'll be beginning some of the basic terms related to the circular motion, right? That will be angular displacement, angular position, angular velocity, and angular acceleration frequency and time period as well, right? We'll be beginning with a very basic discussion about the circular motion, right? So talking about the angular position, right? So you can see here, this is the Cartesian coordinate system, right? And this is the circle, right? This is the circle. Let's suppose on this circle there is a point P or the particle P which is moving in a circular path in this fashion, right? Just moving in a circular path in this fashion, right? So at any time instant or at any instant, let's suppose this particle P is at this position, right? Let the position of this particle be denoted by this coordinate x comma y, right? X comma y. The particle is at this position P, right? Now the origin of this Cartesian system is taken as the reference, right? So with respect to the origin of this xy plane, or with respect to the origin of this Cartesian system, the particle is having the position P, right? Having the coordinates x and y, right? And the reference line here is taken as the positive x-axis, right? Positive x-axis. So the angle subtended by this point P with respect to this origin and with the reference line equal to the positive x-axis. Let's suppose this angle subtended here is the angle theta, right? This is the angle theta subtended here, right? Now this angle theta of this particle P, which is moving in a circular path, right? With respect to the origin of this Cartesian system and reference line, this angle theta we call as angular position, right? It's the angular position. Angular position. So angular position is nothing, it's the angle subtended by the particle in a circular motion with respect to the origin of a Cartesian system with positive x-axis as the reference line, right? So this angular theta will be called as the angular position, right? Now the angular displacement is nothing, it's the change in the angular position, right? So angular displacement we call it as change in angular position. Change in angular position. That will be the angular displacement, right? Change in angular position. Call it as angular position, right? So, or we can say that angle through which the position vector of the moving particle rotates in a given time interval, right? Let's suppose initially the particle was at the reference line, right? At the reference line. So initial angular position here is 0 with respect to the positive x-axis or with respect to the reference line. Now, after some time interval t, the particle is moving in this circular path and it's this point P. Now, the final angular position minus the initial angular position, or we can say the change in angular position here is theta, right? Now, this time, this theta will be the angular displacement, right? This will be called as angular displacement. So angular displacement is nothing, it's the change in angular position of the particle which is moving in a circular path with respect to the origin of a Cartesian system or with respect to the reference line, right? So any angle measured above this reference line from this reference line will be taken as the positive, or the angle measured below this reference line will be taken as negative, right? It's by convention, right? By convention, we can take the angular positions measured below this reference line will be taken as positive or angular, or we can say that the anti-clockwise angles are taken to be positive or clockwise angles are taken to be negative by convention, right? So the change in angular position will be called as the angular displacement of a particle, right? With respect to the origin of this Cartesian system, right? So there are 2 points, one is angular position and another is angular displacement, right? Angular position and angular displacement, right? Now the unit of this angular displacement is nothing, it's the radians, right? We measure the angular displacement in radians, right? Measure the angular displacement in radians. We know that 360 degree is equivalent to 2 pi radians, right? It's equivalent to 2 pi radians, right? Those 360 degree angle in terms of radians is equal to 2 pi, right? So 360 degrees equivalent to 2 pi radians. It means that for one circular path or one complete cycle or one complete rotation, the angular displacement is 360 degree, or we can say the angular displacement is 2 pi, right? So 1 degree angular displacement in terms of radian will be nothing. It will be 2 pi upon 360, right? 2 pi upon 360 degree, or we can say that this is equal to pi upon 180 degree, right? Now let's suppose we have to write theta in terms of radians, right? In terms of radians. So theta here will be nothing. It will be pi upon 180 degree, right? Multiplied by the theta, right? So this will be the theta in terms of radians, right? This will be the value of theta in terms of the radians, right? Now let's look at this question. A particle completes 1/3 revolution, right? 1/3 revolution in 0.6 seconds, right? 1/3 revolution in 0.6 second. Find the time period, right? Frequency and angular displacement after 1.8 seconds, right? So let's suppose this there's a particle which is moving in a circular path, right? There's a particle which is moving in a circular path with respect to the origin of the system, right? With respect to the origin of the system, right? Now you can see that the origin of this circular path is taken to be the reference, right? Or the positive x-axis of this Cartesian system is taken as the reference line, right? Now it's given that 1/3 of the revolution. We know that in a one complete revolution, the particle will cover an angle of 2 pi or an angle of 360 degree, right? 360 degree, right? So if 1/3 of revolution, let's suppose the speed of this particle is constant, or we can say speed is constant here, right? Speed is constant. If the speed of the particle is constant here, right? If the speed of the particle is constant, then 1/3 of the revolution is completed in 0.6 seconds, right? If 1/3 is completed in 0.6 second, right? So 1/3 of revolution is completed in 0.6 second, right? Then the one complete revolution will be completed in 3 multiplied by 0.6, right? So it means that the time taken for the complete revolution will be 1.8 second, and this will be the time period, right? This will be the time period. Time period is nothing, it's the time required or time taken to complete the one complete cycle, right? That's what we call as time period, right? And the frequency is nothing, it's the 1 upon the time period. That's what we call as the frequency, or number of revolutions completed per second, right? That's the frequency, right? Now you can see here the time period is 1.8 seconds, so the frequency will be 1.8 upon 1 upon 1.8, or we can write it as 10 upon 80, right? That will be equal to 5 upon 9 hertz, right? This will be the frequency, right? 5 upon 9 hertz will be the frequency of this particle. Now, the angular displacement after 1.8 second. We know the time period is equal to 1.8 second, right? It means if the particle starts from this point, if the particle starts its motion from this point, right? Then particle, after completing a time period of 1.8 second, it will once again reach at this position, and the angle traveled by this particle, or the angular displacement of this particle, will be nothing. It will be 360 degree will be the displacement, right? 360 degree will be the angular displacement for the complete one revolution, right? For the complete one revolution, 360 degree will be the displacement for one complete revolution, right? So 360 degree is the angular displacement after 1.8 second, because 1.8 second is the time period for this motion, right? Now let's look at this question, right? A student runs 30 meters around a circular track, right? There's some circular track. There is some circular track, right? And in this circular track, a student runs 30 meters around a circular track of diameter 100 meters. If the diameter of this circular track is 100 meters, then the radius of this circular track will be 50 meters, right? Radius of this circular track will be 50 meters. So R is equal to 50 meters, right? The question is that what is his angular displacement, right? But is his angular displacement when the student runs 30 meters around a circle, right? Now you can see, let's suppose the student, this is the 30-meter distance traveled by the student, right? 30 meter, right? And let's suppose this is the theta. Theta is the angular displacement, right? Theta is the angular displacement. The angle subtended at the origin of this circle is nothing. It's given by the arc divided by the radius, right? It's equal to arc upon the radius, right? Now arc is nothing, is the length of the arc, right? And the angle measured will be here in radians, right? It will be in radians. Now the arc is the length traveled by this student, right? It is given as 30 meters upon the radius of this circular path, that's 50 meters. The angular displacement will be here, that will be 3 upon 5 radians, right? 3 upon 5 radians. In terms of angle, right? In terms of angle, we know 2 pi radians is nothing, that's 60 degree, right? 360 degree, right? 360 degree. Or we can say 1 radian is equal to 360 upon pi, 360 upon 2 pi, right? Then 3 upon 5 radians will be equal to the angle of, in terms of degree, 3 upon 5 multiplied by 360 upon 2 pi, right? Upon 2 pi, right? So from here, you can see here it will be 180 upon pi, right? 180 upon pi, that will be 5.3, right? 5.3 and 5.6, that will be 36 multiplied by 3, right? Upon pi, right? 36 multiplied by 3 upon pi, that will be equal to, so it's going to be equal to 108 upon pi degrees, right? It will be in degrees, right? So this will be the angular displacement. This will be the angular. So the angular displacement. So the angular displacement here will be equal to 18 upon pi, 108 upon pi degrees, right? So 108 upon pi degrees will be the angular displacement. Now talking about the angular velocity, right? Talking about the angular velocity, let's see how we actually define the angular velocity. So the angular velocity is nothing, the way we define the way we define the velocity of a particle. It's the rate of change of the position vector, or we can say it's the rate of change of displacement of a particle with respect to time. That's how we define the velocity of a particle, right? In the same way, the angular velocity will be defined as the change of angular position of a particle with respect to time, or we can say rate of change of angular position with respect to time. That's the angular velocity, right? That's the angular velocity. So angular velocity is denoted by omega. It's nothing, it's given by the rate of change of angular position of particle with respect to time, right? Angular position of a particle with respect to time, that's the angular velocity, right? Or we can say the derivative of the angular position with respect to time will give us the instantaneous angular velocity of a particle, right? So this angular velocity we call as instantaneous angular velocity, right? This angular velocity will be called as instantaneous angular velocity. This is nothing, this is instantaneous angular velocity, right? This is the instantaneous angular velocity, right? So d theta over dt, where theta is the angular position. So rate of change of angular position with respect to time will give us the angular velocity of a particle, right? Now let's talk about the average angular velocity. So average angular velocity is nothing. Angular velocity is nothing. It's omega average. It's nothing. It's equal to the change in, or we can say it's the change in or we can say total change in angular position, right? Change in angular position per unit time, right? It's delta theta over delta t, right? So it's nothing, it's the final angular position, right, minus initial angular position upon the time delta t. So this is what we call as average angular velocity, right? This is nothing, this is average angular velocity. So the average angular velocity is defined as delta theta upon delta t, or we can say total angular displacement, right? So average angular velocity will be nothing. We can define it as total angular displacement upon total time. Total angular displacement upon the total time. This will be defined as the average angular velocity, right? Upon the total time. So total angular displacement upon total time is what we call as angular velocity, average angular velocity. That's delta theta upon delta t, right? Now, if this delta t tends to 0, right? If this delta tends to 0, then the angular velocity will be called as instantaneous angular velocity, right? Delta t tending to 0, right? Delta theta upon delta t, right? We can write it as t theta upon dt, right? This is nothing. This is what we call as instantaneous angular velocity, right? This is nothing. This is instantaneous angular velocity. This is what we call as instantaneous angular velocity. This is the instantaneous angular velocity, right? This is the instantaneous angular velocity. Now let's discuss this question, right? A particle revolving in a circular path, right? A particle revolving in a circular path completes first 1/3 of the circumference in 2 seconds, while next 1/3 in 1 second. Calculate its angular velocity, right? Calculate its angular velocity. The question says that the particle moves in a circular path, right? If the particle moves in a circular path, right? Particle moves in a circular path, right? The particle moves in a circular path in this fashion with some speed v, right? Then the question says that 1/3 of the circumference is traveled in 2 seconds, while next 1/3 is traveled in 1 second, right? Now let's look what is this 1/3 of the circumference, right? Or we can say in a one complete revolution, the particle travels an angular displacement of 2 pi, right? It's in one complete cycle. In one complete cycle, the angular displacement of the particle is 2 pi, right? So in 1/3 of the cycle, the angular displacement will be 2 pi by 3, right? In another what we call another 1/3, the displacement will be once again 2 pi by 3, right? So the question says that in first 1/3 of the circumference is traveled in 2 seconds and next 1/3 in 1 second, right? Calculate its angular velocity. So the angular velocity will be nothing, average angular velocity, that's the total angle traveled upon the total time. So the total angle traveled will be 2 pi upon 3 plus 2 pi upon 3 upon the total time. So the total time here is nothing, that's 2 plus 1, that will be 3, right? So it will be equal to 4 pi upon 3 into 3, right? So the average angular velocity, omega average here will be equal to 4 pi upon 9, right? This will be the average angular velocity. We know that unit of this theta is radian, right? And the unit of time is second. So it will be radians per second. So the SI unit of angular velocity is nothing. It's radians per second. So 4 pi by 9 will be the average angular velocity of this particle, right? So let's look at this question, right? A particle is moving with constant speed in a circular path, right? A particle is moving in with a constant speed in a circular path, right? Find the ratio of average velocity to its instantaneous velocity, right? We have to find the ratio of average velocity to its instantaneous velocity when the particle describes an angle of pi by 2 radians, right? The question is like this. The question is like this. The particle is moving in a circular path, right? The particle is moving in a circular path, right? Let's suppose this is the origin, right? If the particle moves in a circular path, right, with some constant speed v, right, with some constant speed v, let's suppose that the particle begins its motion from this point P or from this reference line, right? Now we have to calculate the ratio of the average velocity to its instantaneous velocity when the particle describes an angle of pi by 2 radians. It means that the angular displacement of this particle with respect to this point P is 90 degree, right? 90 degree, or we can say the pi by 2 is the angular displacement of this particle. The particle was initially at point P. Now the particle has reached at the point R, right? The particle has reached the point R. I can see here the angular displacement here is 90 degree, right? But we have to calculate the ratio of the average velocity to its instantaneous velocity, right? By magnitude only, right? By magnitude only. Now you can see here the instantaneous speed of this particle is v, right? V is instantaneous speed, right? It's a constant speed, so instantaneous speed here is v, right? So instantaneous speed is v, right? But the average velocity we defined as v average velocity is nothing, that's equal to total displacement upon total time, right? Total displacement of a particle upon the total time, right? The question is asking about the average velocity, not about the average angular velocity. So this is total displacement upon total time, right? Now you can see here from this position, this was the initial position, this is the final position. So this vector will be the displacement vector, right? This will be the displacement vector, right? So this will be the displacement vector here, right? Now the total angular displacement here for this particle, or total displacement of this particle, will be from point P to point R, right? From point P to from point P to point R, right? I can see here this is the initial position of this particle, this is the final position of this particle, right? I can see the total angular distance, right? The total angular displacement, right? The total displacement of this particle will be given as, that will be 2r sine theta upon 2, right? 2r sine theta upon 2, right? Where theta is the angle traversed by the particle, right? So this delta s is nothing. Delta s will be nothing. This is the displacement, right? 2r sine 90 upon 2, that's sine of 45 degree, right? That will be equal to 2r upon root 2, right? Or we can write it equal to root 2r, right? So this will be the total displacement, right? Root 2r will be the total displacement. This is one way of doing it. Another way of doing is that for 90-degree angle, if this is the radius r, this is the radius r, so this is r, this is r, then this hypotenuse will be nothing. It will be under root of r square plus r square, right? This will be nothing. That will be equal to root 2r, right? That will be equal to root 2r, right? So for this 90-degree rotation, the angular displacement with respect to this point will be root 2r, right? The total time taken from point P to point R will be nothing, because it covers a distance of 1/4 or quarter of a circle, right? Quarter of a circle. The time taken will be nothing. It will be the speed, right? It will be the distance traveled by this particle from P to R upon the speed, right? Now the distance will be 1/4 of the circumference. That will be pi r upon 2, right? Pi r upon 2, right? So the time taken by this particle from point P to point R will be pi r upon 2v, right? Now calculating the average velocity here will be equal to total displacement, that's root 2r upon pi r, right? Multiplied by 2v, right? Multiplied by 2v. So r will get cancelled. We'll be left with the average velocity 2v root 2 upon pi, right? You can write it as 2 root 2v upon pi, right? This will be the average velocity, right? And the instantaneous magnitude of the instantaneous velocity is equal to v. So the ratio, right? The ratio here will be v average upon v instantaneous, right? That will be equal to 2 root 2v upon pi divided by v, right? V and v will get cancelled. So this ratio will be here equal to v average upon v instantaneous. That will be equal to 2 root 2 upon pi, right? This will be the ratio, right? 2 root 2 upon pi will be the ratio. So this is the ratio between the average velocity and instantaneous velocity of a particle moving in a circular path, right? Moving in a circular path. Now let's calculate the instantaneous angular velocity of this particle, right? So if angular displacement of a particle is given by theta is equal to 2 minus 2bt plus 3ct square, right? So theta as a function of time is given as, it's given as 2 minus 2bt, right? Plus 3t square, right? And we have to calculate the instantaneous angular velocity, right? So omega instantaneous is nothing. That's equal to d theta over dt, right? D theta over dt, right? The value of theta is given as a function of time, that's given as 2 minus 2bt, right? Plus 3ct square, right? 3ct square, right? Now taking the derivative here, the derivative of this constant will be 0, and the derivative of minus 2bt with respect to t will be nothing. It will be 2b, right? Minus 2b. And the derivative of 3c2 square with respect to t will be 6ct, right? So this will be the omega instantaneous. So this is the instantaneous angular velocity, right? Now we have to calculate the angular velocity at time t equal to 2 seconds. Now putting the value of, let's put the value of t equal to 2 seconds, we'll get minus 2b plus 6c multiplied by 2. That will be equal to minus, it will be minus 2b, right? Minus 2b plus 12c, right? This will be the instantaneous angular velocity for this particle, right? Instantaneous angular velocity at time t equal to 2 seconds. So the instantaneous velocity is defined as, instantaneous angular velocity is defined as d theta over dt, right? That's the rate of change of angular displacement with respect to time, right? Now let's establish a relation between linear and angular velocity, right? We have to establish a relation between linear and angular velocity, right? So now talking about the direction of this angular velocity, right? So the direction of angular velocity, you can see here in a circular motion, it is always perpendicular to the, it's always perpendicular to instantaneous speed or instantaneous velocity. The direction of angular velocity is perpendicular to the instantaneous velocity, right? We'll see it. Let's derive the relation between a linear velocity and angular velocity, right? You can see here, let's suppose there is a displacement or arc there is a distance covered by this particle from this point P, right, to this point Q, right? Let's suppose this particle moves from point P to point Q and subtends an angle of delta theta, or we can say the angular displacement here is delta theta with a radius r with respect to origin O, with respect to the origin O, right? We know that this angular displacement delta theta is nothing. It will be arc upon radius, right? It will be arc upon radius, right? Arc upon radius. Now the arc here is equal to delta S, right? Delta S upon radius is R, right? Radius is R. Now if we differentiate this equation on both sides, differentiating on both sides with respect to time, right? With respect to time. So if we differentiate the above equation both sides with respect to time, right? Such that delta t tends to 0. Delta t tends to 0, right? Delta t tends to 0. So it will be delta theta upon delta t, right? And this delta t is tending to 0, right? Delta t is tending to 0. So it will be delta s upon r into delta t, right? Where delta t tends to 0, right? Now we can write this equal to d theta over dt, right? D theta over dt, that will be equal to, right? It will be 1 upon r, right? 1 upon r. Del s upon del t will be the velocity v, right? Velocity v. Or from here, we can write d theta over dt equal to omega, right? So from here, it implies that the relation between the angular velocity and the linear speed is nothing. Omega will be equal to v upon r, right? And v will be equal to r omega, right? R omega, right? So this is the relation between the linear velocity or linear speed and angular velocity, right? So v is equal to r omega, right? Now the direction of this angular velocity is always perpendicular to the position vector of this particle with respect to the origin of this Cartesian system and the linear velocity of this particle, right? Or we can say in the vector form, we can write this v velocity, right? It will be r cross omega, right? R cross omega. So the velocity vector will be here. V will be r cross omega, right? V will be r cross omega. The vector relation between the velocity and the omega, that's the angular velocity, it's r cross omega. It means the velocity vector is equal to the cross product between the position vector and the angular velocity vector, right? It's a cross product between the position vector and the angular velocity vector, right? So v is equal to r cross omega, right? Or we can say that velocity vector, right? Velocity vector will be here perpendicular to both the position vector as well as the angular velocity, right? Position vector as well as the angular velocity, right? I can see here, let's suppose this particle is moving along this path, right? In this circular path, right? So this is the position vector of this particle from the origin of this system, right? Origin of this Cartesian system. This is the velocity or position of this particle from the origin, right? This is the position of this particle and this is the velocity vector, right? This is the velocity vector, right? So the direction of direction of direction of omega will be you just curl the fingers right along the direction of the velocity, right? Along the direction of the velocity vector, right? Then the thumb of your right hand will point in the direction of the omega, right? It will point in the direction of omega, right? So v will be equal to r cross omega, right? So this was the relation between uh, angular velocity and the linear velocity, right? If we curl the finger, right? If we let's suppose this is the omega along this direction, right? Omega, right? If we curl this finger, right? If we calculate this cross product between the omega vector and r vector, right? So this omega and r vector will be directed along this velocity vector, right? V. That means that it should be v should be equal to omega cross r, right? It should be v is equal to omega cross r, right? Then it will be consistent with the equation, consistent with the direction of the angular velocity and direction of the velocity, right? So V is equal to omega cross R, right? So V will be equal to omega cross R, right? Omega cross R. Now let's solve this question. An insect moves in a circular path of radius 25 upon pi centimeter, right? An insect is moving in a circular path of radius 25 upon pi centimeter steadily and completes 10 revolutions in 50 seconds, right? We have to calculate its angular speed and average linear speed of the motion, right? So the average angular speed will be equal to, right, average linear speed upon that radius, right? So we'll be calculating the average angular speed, that will be equal to average angular speed omega, that will be equal to total angular displacement delta theta upon the total time, right? Now it's given that the particle is actually or the insect here is actually completing 10 revolutions, right? 10 revolutions, right? It's completing 10 revolutions in 50 seconds, right? It means the total time is 50 seconds, or we can say this particle, if it completes 10 revolutions in 50 seconds, then the one revolution of this particle will be completed in 50 upon 10, that's equal to 5 seconds, right? So the particle will complete the one complete revolution in 5 seconds, right? One complete revolution in 5 seconds. Now the angular velocity, average angular velocity, will be nothing, that will be 2 pi upon the time period, right? 2 pi upon the time period, right? So in one complete revolution, it will cover an angle of 2 pi with a time period of t, right? The time period is given here, that's 5 seconds, right? That's 2 pi upon 5. So this will be the average angular velocity, 2 pi upon 5 radians per second, right? Radians per second. We know that V is equal to R omega, right? V is equal to R omega, or we can say that in the vector form, V is equal to omega cross R, right? Omega cross R, right? So here R vector is the position vector of the particle with respect to origin of a Cartesian system, and omega is the vector, angular velocity vector, right? Which is perpendicular to both position vector as well as which is perpendicular to both position vector and velocity vector, right? Now you can see here V is equal to R omega. The average angular velocity is 2 pi upon 5. So the average linear speed will be R multiplied by 2 pi upon 5, right? And the radius of this particle is given as 25 upon pi, right? 25 upon pi, right? In the units of centimeters, right? In the units of centimeters, right? But we have to calculate this average velocity in terms of meter per second, right? So we need to convert it into it will be 25 upon pi, right? 25 upon pi will be the radius, right? Multiplied by or divided by 100, right? Divided by 100 and multiplied by 2 pi upon 5, right? So it will be 4 here, right? Pi and pi will get cancelled. So it will be 2 upon 20, right? Or we can write it as 1 upon 10 meter per second, right? That will be equal to 0.1 meter per second. So it means that this insect is actually moving with a linear speed of 0.1 meter per second, right? So this is the speed of the insect, right? And we calculate the average linear speed with the help of the average angular velocity using the equation V is equal to R omega, right? Now let's talk about the angular acceleration, right? Angular acceleration, right? The angular acceleration is nothing, it will be defined as the change in the angular velocity, right? If there is a change in angular velocity, right, either the magnitude of the angular velocity vector change or the direction of the angular velocity vector change, then there will be angular acceleration, right? Then there will be angular acceleration. So it will be defined as the rate of change of angular velocity with respect to time. So angular acceleration alpha is nothing, it's d omega over dt, right? D omega dt. This will be called as instantaneous angular velocity, right? This is nothing. This is instantaneous angular velocity. Instantaneous angular velocity. So it will be instantaneous angular velocity, right? So instantaneous angular velocity is defined as d omega over dt, right? That's the rate of change of angular velocity with respect to time, right? Now talking about the average angular velocity, it's nothing. Alpha average, that's the change in angular velocity vector, right, upon the total time, right? So it will be delta omega vector upon the delta t, right? Delta omega vector, right, upon the delta t. So this is nothing. This is average angular velocity, right? Average angular velocity. average angular velocity, average angular acceleration, not velocity. This will be average angular acceleration. So the average angular acceleration is defined as final angular acceleration, final angular velocity minus the initial angular velocity upon the time interval, right? So omega final minus omega initial upon delta t will give us the average angular acceleration, and d omega upon dt will be the instantaneous angular acceleration of a particle, right? Now let's derive the different equations of motion, right, for a circular motion, right? We know that in case of motion along a straight line or motion in two dimensions, right, we derived the equations of motion, right, which were based on the fact that the acceleration of a particle should be constant, right? Acceleration of the particle should be constant. Then we arrived at certain equations of motion, right? In the same way, we will be deriving the similar equation for the circular motion as well, with the fact that if the angular acceleration is a constant, right, angular acceleration should be constant, right? Angular acceleration should be constant. If angular acceleration is a constant quantity here, right, then we can arrive at some results, right, for the circular motion, right? So angular acceleration is defined as alpha, that's t omega over dt, right? T omega over dt, right? Now, if we integrate this alpha with respect to time t, right, that will be alpha dt will be equal to d omega. Integrating it on both sides, let's suppose at initial time t1, or we can say at time t equal to 0, right? The initial angular velocity of this particle was omega I, and there are some angular velocity at some final time t, right? At some final time t. Now, integrating it, alpha is to be assumed constant, right? So it will be alpha t, that will be equal to omega final minus omega initial, right? Or we can write here the final angular velocity will be nothing, that will be initial angular velocity, right? Omega I plus alpha t, right? Plus alpha t. So this equation is only valid if alpha is a constant. Alpha is a constant, right? Alpha must be constant, then only we can use such equation for circular motion, right? So omega final is equal to omega initial plus alpha t, right? That's the angular velocity, right? That's the final angular velocity, or we can say the first equation, right? Similarly, we can write the equation alpha equal to, that's d omega over dt, right? That's the first derivative of the angular velocity with respect to time, or second derivative of the position vector, sorry, angular position with respect to the time, right? Or we can also write it as omega d omega by d theta, right? Omega d omega upon d theta, right? It can also be written in this way, right? Let's suppose it's d omega upon d theta here, right? Then multiplied by d theta upon dt, right? So d omega upon d theta, right? D theta upon dt, we can write it as omega, right? So we arrive at this equation omega d omega upon d theta. So let's integrate this equation on both sides with respect to theta. That's alpha d theta should be equal to omega d omega, right? Now integrating on both sides, right? So let's suppose initially the angular displacement here was theta, angular position here was theta I, right? The final angular position is theta final, right? Initial angular velocity is omega I, and the final angular velocity is omega final, right? We'll get the result, integration of omega with respect to omega, it will be omega square upon 2 with the limits omega initial to omega final, right? Now we're left with alpha delta theta, that's equal to omega final square minus omega initial square upon 2, right? Upon 2. So from here, omega final square will be equal to omega initial square, right? Plus omega final square will be equal to omega initial square multiplied by twice alpha delta theta, right? So this will be the equation, right? This will be the equation. This is the another equation of motion for this circular motion, right? So there are two important equations, right? One is omega final will be equal to omega initial plus alpha t, and omega final square plus omega initial square, that will be equal to twice alpha delta theta, right? That will be equal to twice alpha delta theta, right? Now, similarly, we can have this equation as well, right? We can have this equation as well. We know that omega is equal to omega naught plus alpha t, right? Alpha t. And omega, initial angular velocity will be a constant here, right? And now omega, we can write it as t theta over dt, right? T theta over dt, that will be equal to omega naught plus alpha t, right? Now, integrating the equation on both sides with respect to time, and on the LHS, it will be with respect to theta, right? So it will be omega naught dt plus alpha t dt, right? Alpha t dt. Now integrating on both sides, right? Integrating on both sides from theta initial to theta final, right? The final angular position minus the initial angular position will give us the angular displacement delta theta from time 0 to t, right? From time 0 to t, right? So it will be omega naught t plus alpha is a constant. The integration of t with respect to t will be t square upon 2 with the limit 0 to t, right? We'll be left with the equation omega naught t, right? Plus alpha t square upon 2, right? So the angular displacement delta theta has to be equal to omega naught t plus alpha or half of alpha t square, right? So this will be the third equation, right? This is the third equation for the circular motion where angular velocity, angular acceleration is a constant, right? So alpha must be a constant, right? Alpha must be a constant to use this equation, right? Otherwise, we cannot use this equation for the circular motion. Alpha must be a constant quantity, right? So these are the three important equations, right? Based on these equations, we'll be solving some of the questions in the next lecture, right? And we'll be further discussing about the circular motion in the next lecture, right? So we'll stop here, right? We'll meet in the next section. Till then, take care and goodbye.